developed this proximal algorithm in variable exponent Lebesgue spaces, and it is a joint work with my advisors, Claudio Statico and Luca Peatroni. The goal of today's talk is to define a forward-backward algorithm to solve an optimization problem that can be written as the minimization of the sum of two functions, f and g, where f and g are both lower semi-continuous, proper and convex, and f is also differentiable. And we want to solve this problem in a variable exponent Lebesgue space. That is not the usual context we see this kind of problem, and it is a Banach space, and instead of measuring the norm of an element with a constant exponent p, we consider a variable exponent that is pointwise variable. So the outline of the talk is this. At first I will introduce some basics elements of the variable exponent Lebesgue spaces, and then I will move on to the resolution of the optimization problem. At first in the Hilbert space scenario, and then I will present some problems that arise when we move to the Banach space scenario, and I will present an algorithm in the Banach space, and then the generalization into the Lebesgue space with variable exponents. So, what are variable exponent Lebesgue spaces? In the classical LP spaces, we have a constant exponent p, and in this other context, we have the Lebesgue measurable function that is defined from the domain to this interval 1 plus infinity. For simplicity, I will assume p to be always less than plus infinity. And in classical LP spaces, we can define the norm in the usual way, and the problem that arises when we want to define the norm in the variable exponent Lebesgue space is that we don't have a clear choice for computing the radical. And also, since we don't have a clear definition of the norm, we don't know how to define the elements of the space. The first problem is to solve the definition of the norm. We cannot compute the radical, but we can compute, in both cases, the integral that is inside, and this quantity is called modular, and it is a very important function in this other in the Lebesgue variable exponent spaces. An important remark is that if the variable exponent is constant, the modular coincides with the norm of x to the power of p. We want now to use this quantity, the modular, to define the norm in these spaces. And to do so, let's first consider an element of an LP space with p constant and a scalar lambda. And let's compute the modular of x over lambda. This quantity is equal to 1 over lambda to the power of p times the norm of x to the power of p. And so we can observe the following. So if lambda is equal to the norm, this quantity is equal to 1, and if lambda is larger than the norm, this quantity is less than 1. And the important thing to note is that lambda equal to the norm is the smallest scalar satisfying this inequality. And I've shown you this because this is exactly the definition of norm in a variable exponent Lebesgue space. So the norm is called Luxembourg Norm, and it is defined as the infimum of the scalars that such that the modular of x over lambda is less than or equal to 1. And if such scalar doesn't exist, the norm is plus infinity. And now we can also define the elements of the space. So this space is the set of the Lebesgue measurable functions such that the norm is less than plus infinity. And it is a Banach space with the Luxembourg norm. Let's now focus on the resolution of the optimization problem, at first in a Hilbert space. So it is the usual context, and the algorithm that is used is the proximal splitting algorithm or forward-backward algorithm. And as hypothesis, we have the Lipschitz continuity on the gradient of f, and we choose the step size accordingly. And the updating rule is what you can see in the slide. Let's see it more in detail. So the first step we have to do is to compute is the forward step or gradient step, and it depends on the smooth function f, and basically we move into a descent direction for the function f. And then we want to compute also a step that decreases the value of the function g, and this is done by a proximal step defined in terms of the proximal operator that basically tell us that we are decreasing the values of g but staying close to the steps we have just computed before. And now we want to, with this in mind, define an algorithm in the Banach spaces first and then in the variable Lebesgue spaces. So the first problem that we have is that the dual space in the Banach spaces is no longer isometrically morphed to the space itself. And then we also do not have the scalar product. So the dual space is a space of functionals, and so the elements of this space, x star, can be evaluated at a point of the space x, and we indicate this operation with the pairing notation that is very similar to the scalar product in terms of notation. And since x star is linear, we can, let's say, think of this operation as the scalar product. And then we have that the subdifferential that is defined as follows is a multivalued map from x to x star. And so the elements of the subdifferential are elements of the dual space. And this is a problem since we have to compute a forward step, and the gradient is an element of the dual space. So as I was saying, we have to compute xk minus the gradient, but these two elements live in two different spaces, and so we need a solution to this. And the solution are the duality mappings that are defined in the next slide, that are basically link the primal and the dual space. So we have a map from x to x star and a map from x star to x. And we can compute the gradient step in two different ways. The first one is the dual gradient step, and so we choose to compute the gradient step in the dual space, taking the iteration xk and computing the duality map of xk that lives in x star, and then computing the difference. And the other solution is to compute the primal gradient step, and so to take the gradient of xk, of f at xk, and move it to the primal space with the duality map. So this is the definition of duality mapping that depends on a parameter r through a Gauge function that is t goes to t to the power of r minus 1. And what is used in practice is not the formal definition, but the Asplund theorem, that basically tell us that the duality maps are the subdifferential of the norm, not really the norm, but 1 over r times the norm to the power of r. Here are some examples. So in Hilbert spaces, the duality mappings are the identity if the parameter is true, and then we have the duality mappings of LP spaces that are defined as you can see, and the duality mappings of LP variable spaces. Here the expression becomes more complicated, but I want to point out that if the exponent is constant, basically we have the same definition as in the case of LP space, because what you can see in blue is the same that we have on the line above, and then the sum is equal to 1 if the constant, if p is constant. Let's now see what happens in Banach spaces. So first, you may wonder why we need to define such an algorithm in Banach spaces. And since we often come up with the optimization problem of the kind we are trying to solve in inverse problems, when we solve these problems in an inverse space, the solution is often too smooth and not too sparse, and the discontinuity are difficult to retrieve, whilst the Banach spaces, even if are more complicated to treat, reconstruct better this type of discontinuity. So here we have the optimization problem in Banach spaces, and the main reference for the next slide is this paper from Guan and Song, where they present a forward-backward splitting algorithm in Banach space scenario. And the hypothesis they make on the gradient of f is no longer the Lipschitz continuity of the function, but the p minus 1 order continuity of the gradient. So, as you can see by the inequality that defines this property, it is very similar to the inequality that defines the Lipschitz continuity of the gradient, but we have on the right side we have this power to the p minus 1 that before was not present, and this is caused by the duality mappings that depends on this power to the p minus 1. And the step size is again chosen depending on the parameter p and k that define the order continuity of the gradient of f. So the updating rule is the one in the box, and it is slightly different from the Hilbert case one. And let's see now the steps separately. So the first one is a dual gradient step, as I showed you before. So we compute the gradient in the dual space. And the proximal step goes from the dual space to the primal space, and it is defined in terms of a proximal operator depending on both g and the distant function delta, but is defined, as you can read, and it is a Bregman-like distance. So instead of having the distance between x and u, but before was the distance in an inverse space, so it was the norm of x minus q. Now we can't do the same because we have to compute the distance between an element of the primal space x that is x and the element u star that is in the dual space x star. So let's see now again the steps that we have to compute. So at first we have to compute the duality step, so we take xk and move it to the dual space with the duality maps. Then we compute the dual gradient step, and then we compute the proximal step, and so if we plug the definition of prox and the definition of distance delta, we retrieve the updating rule that I showed you in the slide before, in the bottom line. Let's see now an example. So as I mentioned before, we have this type of optimization problem when we want to solve an inverse problem. So we consider a linear operator A from LP to LP, and an observation, and a noisy observation Y in LP. And we want to solve AX equal to Y. To do so, we consider a Tikhonov functional with a smooth function f, that is the norm of AX minus Y to the power of P, and a regularization term G that is the L1 norm. And we want to solve this problem with the algorithm just seen. So to do so, I recall the definition of duality maps, that is the one in green, and then in pink you can see the gradient of f evaluated at xk. That is an element of LQ, since LQ is the dual of LP. And if we plug this quantity into the updating rule, we can see that we can go from an n-dimensional optimization problem on the first line to a one-dimensional problem in the third line, since all of these quantities are separables, and we can easily see that what we have in the last line only depends on the ith component and not on the others. And so we can treat each component independently from the others and define one-dimensional function that you can read here and solve a one-dimensional optimization problem. Let's see a comparison between the Banach space one-dimensional problem and the Hilbert space one-dimensional problem and their solutions. So these are the thresholding functions that we obtain as solution of the one-dimensional problem that was in the slide before. And in the plot you can see how the action of this thresholding function is different. So the one in red is the usual soft thresholding, and the one in blue is, let's say, the soft thresholding in a Banach space scenario where the action is not linear. Now we can move on to the proximal algorithm in variable exponent Lebesgue spaces. And again, why we want to consider these spaces, the answer is that sometimes we need spatially variant regularization and spatially adaptive regularization. And instead of defining complicated regularization term, we can consider an inverse problem in a different space, but for its geometrical properties has this adaptive feature itself. So the problem is again the same, and the question is why we need a new algorithm, because this space is a Banach space and we have just seen a Banach space algorithm, and the answer here is that the norm that appears in the algorithm in green cannot be computed directly because we don't have a closed form expression, but to obtain the norm in this space we need to solve a one-dimensional optimization problem. And this is computationally expensive when you have to do it many times during the resolution of an algorithm. And the norm is also not separable, so we can't use the trick that I showed you before to go from a n-dimensional problem to a one-dimensional problem. And not only the norm is not separable, but also the duality mapping, since it depends on the norm. And so we have also to compute the norm to compute the duality mappings. And this is a problem, and it makes the algorithm impractical. So the solution is to replace the norm with the modular, since it is easy to compute and it is separable, and to replace the duality mapping, that is the gradient of the norm, with the gradient of the modular, that is defined, as you can see, in blue. And these both quantities are easier to compute and separable. And so this is the key idea of the following slides. Again, we have to make an hypothesis on the gradient that is the same as the one before, and the choice of the step size, again, is the same. And here we have the updating rule in a variable exponents Lebesgue spaces scenario, and instead of having the norm of x, we have the modular of x, and instead of having the duality maps of xk, we have the gradient of the modular evaluated at xk. And again, we compute a dual gradient step, and the proximal step depends on distant function delta that is defined as the modular of x minus u star at x. So again, we replace also in this distance the rule of the norm with the modular of x. So this is to show you that if we compute these steps, we obtain the updating rule that I showed you before, exactly as in the Banach space case. And then we see an example. So instead, here we have a linear operator that goes from LP variable to LP, and an observation that lives in LP. And we want to solve the optimization problem, the inverse problem AX equal to Y. And again, we consider the Tikhonov-like functional, as before, defined with F smooth, norm of AX minus Y, and to the power of P, and we have G, that is the L1 norm. And we use the algorithm that I just showed you with the modular. If we recompute these steps, substituting the gradient of the modular in green and the gradient of F, and plugging them in, we can see that this algorithm can be used in practice, since, again, these quantities are all separable, and each element of the sum depends only on the ith component, and so we can again define a one-dimensional functional and minimize it at each iteration. So this is very similar to the one we have seen before. And to conclude, I want to show you a numerical test. These are very preliminary results, and we have in the top left corner the true data x, and in the bottom left corner the observation that is nothing but the integral or sum of x, and we want to solve the problem of finding x given y in three different scenarios: in the Hilbert space L2, in the Banach space LP with p equal to 1.8, and in a variable exponent Lebesgue spaces LP variable. You can see in red the reconstructions in the top line, and in the bottom line you can see the sum over the integral of the reconstruction compared to the actual integral of the data. So if you only look at the bottom line, the best reconstruction seems to be the Hilbert one, but if you look at the top line, you can see that the one that factors reconstruct the intensity of the spikes is the one in the variable exponent Lebesgue space in the right top corner. And here I have some numbers that are the errors computed on x and computed on y. So if we only look at the integrals, we have that basically the L2 and LP variable cases are very similar. But if we look at the errors measured on x, the best one is by far the variable exponent Lebesgue case. And the plot here is the exponent we have chosen in the variable exponent Lebesgue case that goes from 1.7 to 2, and it is chosen from the L2 reconstruction. Thanks for the attention.
Thank you very much for the amazing talk. Are there any questions from the floor? Okay, 2 questions. Let's start with Nastya.
I'm wondering that you asked for gradient f to be local or continuous. And why it is essential?
It is needed to prove the convergence of the algorithm. Actually, I haven't showed you the convergence, but we have proved it.
But do you need like separability of variable exponent space?
Sorry?
Do you need it for separability of variable exponent space?
No, we need this hypothesis on the gradient of f, both in the Banach space and in the variable exponent Lebesgue space, only for the convergence analysis of the algorithm. So to prove convergence, this hypothesis is crucial, otherwise you can't conclude a sequence of inequalities that leads to the convergence rate of the algorithm.
Do you think to consider modular spaces in general, not only variable exponent, but also include Morley spaces and so on?
So far, I have only focused on this kind of spaces, but maybe in the future.
Okay, then maybe we can discuss it later.
Okay.
Thank you. Any other question from the floor?
Thanks for the talk. I have two questions. So, what is if you computed it? So, what is the convergence rate with respect to your step size? I'd like to know that. And is it possible to recover convergence if you lag your gradient in the computation of your proximal? So you do like gradient descent, right? You have your point and you subtract your gradient. But if you lag it and evaluate it in your previous iteration, or as in an explicit computation.
So the convergence rate is 1 over k to the power of p minus 1. So if p is equal to 2, we recover the convergence rate of the Hilbert case. And as for the last question, what do you mean by lag?
So show me the evaluation of your proximal, even in the first slides. There it is. So when you do the gradient step, you compute xk minus. You have to only evaluate your gradient. You don't have to invert with respect to it. You have to compute a matrix or anything.
No, I have only to evaluate the gradient at xk.
Okay, then nothing. Thanks.
Fine.
Thank you. There is any other question from the floor? Okay, if not, actually, I have a question. And that would be, so let's go into the very classical Banach space, LP space, with P not depending upon anything. And what happens is, often you might have like an energy functional that you want to minimize there, maybe a Bose functional, something that you know your existence. And you know that it lives in an LP space. What engineers do usually is that they do a Newton iteration with the Gattol derivative. Is this convenient? Is this better? And why?
So actually, I don't know. I've only studied the convergence of this algorithm, and I'm now focusing on the numerical test. So I've just done some basics test on one dimension, and I will in the future move to the study of the actual application of these algorithms.
Thank you very much.
Thank you.